Alright, so we're back. Woohoo! With 8.9a. 8.9a means you need to be able to describe the development and evidence that supports plate tectonic theory. Remember, good old scientist Alfred Wegener? He came up with the theory of continental drift. And continental drift was a great thing. He had lots of evidence to prove that the continents had moved over time. And it is true, we did have a supercontinent Pangea. So he provided a lot of good evidence that continents had moved. The problem with his theory, continental drift, was he could not explain how continents moved. So continental drift was replaced with the theory of plate tectonics. Which tells us that plates do, tectonic plates, these large lithospheric plates do move, and they move in different directions, causing different results on the surface of the Earth. So, thanks to Alfred Wegener, we were able to actually move quickly and swiftly from one theory into one that actually is explainable and visible on the surface. So let's look at a little bit of that. If you don't recall the Earth's interior, well, the most important part to this theory is truly the crust. And the crust is the outermost layer of the Earth. But beneath the crust is also another hard layer, rock layer. So these two are solid rock. And they are referred to together as the lithosphere. Lithos means rock. Now, on top of the lithosphere, you'll find all the different sediments and everything until you find way somewhere up here our little homes and gardens and our school and whatever, all the buildings around and roads and cars. So there you go. It's all up on top of here. Okay. So now that we kind of know what's going on, so below the crust, and this is what's kind of the important part here, is a very soft, molten rock area. This is the upper part of the mantle, and it's all melted down rock. And we remember when we talked about how warm and cool or temperature differences in a fluid cause motion. Well, that's exactly what we have going on here. The deeper you go, the hotter it gets, okay? So even though this is upper mantle, this is mid mantle, and so on, the deeper down you get, the hotter it gets, going towards the core, right? So we know this area is hotter than, let's say, the area above, closer to the crust, closer to Earth's surface. So this hot area here is less dense, right, because it's hotter. So this magma rises here, and when it reaches the lithosphere, the top of the upper mantle, it cools here because it's cooler, and it sinks. So here's where our convection currents are going on. This layer is known as the asthenosphere, and it has convection, these circular currents. And what's going to happen, these currents, this convection and gravity, help move plates. And by plates, we're meaning that lithospheric crust. Okay? Alright, so let's see how this works. So let's say we have divergent plates. Let's start off by divergent plates. So divergent, if you can remember, dive away. Okay, they are moving away. So here's some crust and that rigid underlayer, the whole thing called lithospheric crust. And here's some. Well, here's below it, remember, is that molten rock. So here's these convection currents. Got warm stuff rising. And when it gets to that upper part of the crust here, it's going to sink and cool. So you can already see how I've drawn these convection currents, that they could be moving these two away. So these two crustal plates are moving away from each other. That's divergent. Usually this is going on in the middle of the ocean. And that's why we call it a middle ocean ridge. Okay? We have stuff creeping out here, that molten rock coming up here and cooling. And this is actually happening between the North American plate so we're on this side, this is us, North America sits on the North American plate, and the Eurasian plate sits over here. So every year Europe is getting about this much further, 3 centimeters further from the North American plate. So we're moving further and further from North America. So this is going on in the middle of the Atlantic Ocean. Our example would be the Mid-Atlantic Ridge. Another name given to this movement here, and it's real easy to remember, is remember if this is on the ocean floor, right? Ocean. It's on the ocean floor. And the floor, literally the floor that's carrying the ocean is cracked here. New stuff is moving up, hardening, but moving these plates away. New ocean floor is being created all the time. So this is also known as, aka also known as, seafloor spreading. Okay, so that is divergent. There's another type of divergent that occurs beneath continents. The best example here close to home is actually an extension of the mid-ocean ridge. If you look at Iceland, so let's look at Iceland. Iceland is an island, right? And you would follow on the map the mid-ocean ridge. Well, guess what? It's cutting right into Iceland. Okay? So here's the Atlantic Ocean. This is the mid-ocean ridge, or the mid-Atlantic ridge. And there's Iceland, and it's just cutting right through that little island. So that means that one side of Iceland is moving with the North American plate, and one side of Iceland is moving with the Eurasian plate. Meaning that one day, that Iceland will be 2 islands and not just one, right? Because this is on the Eurasian side, and this is on the North American plate. So when a divergent boundary goes through a landmass such as this, it's called, what it creates on land, and what we call this crack. If you were to stand there in Iceland, you can stand right here. You can have 1 foot on the Eurasian plate and 1 foot on the North American plate. Now, not always, you won't be always able to do that, but today you could still do that. Anyway, what we call this crack on land, it's called a rift valley. and Iceland is our example of a rift valley. Alright, so much to divergent plates, plates that dive away from one another. Let's talk about plates that are actually coming together. Convergent plates. They come together. Okay, so we're drawing our picture of our lithospheric plates. The crust below it, the upper mantle making the lithosphere. And here's a plate boundary right between the two. You can see these plates are coming together. Okay, meaning that the currents beneath them in the asthenosphere are most likely pulling them together. So where you have warm rising, here you must have that cool falling, pulling these two together here in the center, right? Alright, so they're coming together. Let's say these are both, on this is both crust that carries land or continents. We're going to call this continental crust. And continental crust. So these are both kind of the same densities, made up mainly of granite rock. So what's going to happen when these two collide or come together? They're going to actually form mountain ranges. So as they come together, things start to buckle in the middle, and what you see forming are mountain ranges. So they buckle and form mountain ranges. Well, our example of that is a mountain range that is still forming to this day. Our example is the Himalayan mountains. I don't know if I spelled it right. Let's just say I did, and abbreviated mountains. Himalayan mountains, so that's our example of this. Now, when we have convergence, and one plate is denser, so this is convergence land, and then usually in general it's going to be convergence land ocean. Convergence, once again, coming together. So land rock is usually less dense. So if we have our lithospheric crust, and let's say this is our oceanic crust, so this lithospheric crust is carrying the ocean on top of it. Over here we have continental crust or land crust. Okay, so when these two come together, this one is denser. The crust is denser. So this is less dense and this is denser. Remember, denser things are always going to sink. And that's the key to what's going to happen here. These can't come together equally. This one is so heavy, it's going to go and dive beneath the other one. So this one's just going to keep going, basically moving. It won't be affected at all. It's not going to go up or anything. It's just going to keep moving, but this one's going to go down and dive beneath the less dense crust. This is movement, or this going under of one plate below another, is called subduction. Now, remember what's beneath the crust. Beneath the crust is that ooey gooey molten rock, the asthenosphere, right? That's got that molten magma. So this is the asthenosphere. So at this point, as it subducts, it's going to be in that ooey gooey molten part, and it's going to start to melt. So it's going to melt down the crust, right? It's going to become ooey gooey molten rock as well. And as it melts down all this incoming crust, a big old pot of magma builds. So the magma builds up. So and what happens, it kind of squeezes in below the land crust and ultimately ends up visible at the surface as volcanic mountains or volcanoes. Okay, so when you see subduction of a plate, so one going under the other, subduction equals volcanoes. No matter if, like on the test, we saw the little island arc, they had some volcanoes. If you see volcanoes, we're talking subduction, we're talking convergence. Convergence and subduction equal volcanoes. There's the key. All right, we're going to do one more. And we're going to talk about transform boundaries. So number 3 would be transform boundaries. So here, where the two plates meet up, here they are. Here's that crust. Here, instead of, this is crust, right? Those lithospheric plates or crust. Instead of wanting to move together or move away from each other, they're actually transforming, meaning they are going to slide past one another. So transform means to change, right? And change it will. Think about it. If one side of the room is trying to move past the other side of the room, what's going to happen to the room? Well, you're going to have a big crack in the middle, obviously. That crack would be called a fault. Right? And as these two plates just stress and they're tight together, huge rock layers, and when they finally do break apart, all that tension and stress is relieved. Well, think about it. Before the break, or before the plates actually move apart, move or slide past one another, all this stress builds up, right? Another word for what's building up is potential energy. Or stored energy, right? Once they actually move past each other, so as soon as they move, we're releasing kinetic energy because it's changed into motion now. And because they're moving past each other, sliding past each other, just think of it, if I had a crack right here and I can actually move these two, they're going to shift and change the whole top, right? If these are the two plates and then they move past each other, now the whole room has changed. Everything's changed. It's not in the same place where it was. That's the whole transformation part. So it's one, now it's all messed up. So the changes along the surface. What has happened here? Well, we've had an earthquake. Surface has shifted. And our example for a transform boundary here in the United States, we have a great example, and it is the San Andreas Fault. The fault is that crack, and along that crack takes motion. Motion takes place because the plates are trying to move past one another. All right, and that would be it for plate tectonics.